To understand how computers process a standard number like 165 or a negative value like -44, we have to look at how data is structured within the hardware. Computers rely on base 2, or binary, because they operate using transistors that only have two physical states, on or off. This is exactly the reason why we must translate our human base 10 numbers and programmer-focused base 16 hexadecimal into ones and zeros. This is the structure of a standard 8-bit register. Because it is binary, the place values double as you move from right to left, starting at 1 and ending at 128. Learning how numbers map into these columns allows us to calculate exactly how much space a piece of data occupies in memory. To convert the denary number 165 into binary, we use the subtraction method. Since 128 fits into 165, we subtract it, leave a remainder of 37, and place a 1 in the leftmost box. We repeat this for every column. 64 is too large for our remainder, but 32 fits, leaving 5. After accounting for the 4 and the 1, we fill the empty spots with zeros. The final 8-bit integer is 10100101. Because binary strings can become very long, we use hexadecimal to group them into 4-bit sections called nibbles. Each nibble is calculated as its own value. Here, 10 becomes A, 12 becomes C, and 4 remains 4. Grouped together, the hexadecimal representation is AC4. Pause the video and try converting the hex string 3ED back into binary. You can see the mapping for each character here. 3 becomes 0011, E becomes 1110, and D becomes 1101. Hexadecimal doesn't change the data the computer is processing. It simply provides a structural shortcut that makes code easier for humans to read and debug. Handling negative numbers like -44 requires a specific process called 2's complement to encode the negative sign using only ones and zeros. A common mistake in exams is converting the number to a truncated 6-bit string and writing it backward. If the string isn't padded to a full 8 bits first, the conversion will be incorrect. The correct method starts by finding the positive 8-bit version of 44. Once you have that padded string, you invert the bits, changing every 0 to a 1 and every 1 to a 0. Finally, you must add 1 to that inverted string. This shifts the final bits to resolve as 11010100, which is the correct negative representation. This shows that even if your math is correct, failing to follow format constraints like 8-bit padding will cause the entire algorithm to fail. Binary addition adds right to left, carrying ones over. A carry in the leftmost column pushes outside the 8-bit register. This overflow error means the calculation exceeded allocated memory. Logical shifts also manipulate values. Shifting left multiplies, shifting right divides. This summary slide covers the essential rules for the exam: the mapping of hexadecimal letters A through F, the 3-step 2's complement process, and the mandatory requirement to pad all strings to 8 bits. Understanding these rules allows you to predict how a computer will handle data and identify errors in memory management. To practice these steps, complete the final trace tables in your workbook.